This video concerns chapter 11, which is on fluids at rest. Remember, when we say static, we mean at rest. So in physics, we normally think of matter as existing in one of four phases or states. We talk about the solid state or the solid phase, where the material is arranged in some orderly manner. We talk about liquids. Sometimes we say that as a fluid. So liquids and fluids are sometimes, well, a liquid is a subset of a fluid, and you'll see why a little later on. And then gases. Gases are subsets of fluids. So liquids and gases both conform to the size of the container they're in, and that's what makes them a fluid, and they move as a bulk material. Plasmas in physics are charged gases. So the gases that surround the Earth's upper atmosphere have electric charges in them, and in fact that's one of the reasons why you have the northern lights. When charged particles from deep space enter the Earth's atmosphere, they excite the molecules in the plasma, and it creates an electric phenomena that results in a light display. The color that you see in the aurora depends on which gases are being energized. So these gases are exactly like the kinds of gases you find in fluorescent light bulbs, only obviously different materials and in a different location. Okay, so solids, liquids, gases, and plasmas. The temperature and the pressure control what state of matter we have. So obviously, if the material is cold, it's almost always a solid. Warm it up a little, it becomes a liquid. Get it even warmer, we get gases. Energize it, you have plasmas. Density is mass divided by volume. And in physics, we symbolize density by the Greek letter lowercase rho. I want to show you how to draw that because so many of you do a really poor job. So it's a lowercase rho. It looks a lot like a little p. It looks a lot like a little p, but most people start with the tail and come up and over. And so, or I guess a little bit like a 9, but it falls on the line. Another one, you might draw it maybe with a little bit more curve to the tail. I think I've told you before, it's awfully hard. Ooh, I don't know that my row looks any better that time. So normally the tail does not come straight down, but it curves a little bit to the right. I'm not sure that either one of my rows that I've drawn for you look especially great, so we will get rid of them. But you need to practice that. It is not a P. So density is mass divided by volume, little rho, little m, capital V. Density is measured in kilograms per cubic meter if you've got MKS units, or grams per cubic centimeter for CGS units. The density of water is 1 gram per cubic centimeter, and that's the same as 1,000 kilograms per cubic meter. You need to know this number. You need to know this, just like you need to know that little g is 9.8 meters per second squared. In case you're wondering how I got from 1 gram per cubic centimeter to 1,000 kilograms per cubic meter, you can see the conversion right here, and I'm not going to go over it for you. I assume you can read. So volume may be given in liters. Volume may be given in liters, where 1 liter is 1,000 cubic centimeters. I don't particularly like to work with liters, and so we'll probably stick with cubic meters and cubic centimeters. Specific gravity is the ratio of the density of the object to the density of water, and it doesn't have any units on it. It doesn't have units. So if I told you that the specific gravity of lead was 13, then that's true whether you're used to using MKS units or CGS units or any other, or even British units, which is what makes specific gravity so useful, is that you don't have to attach the units to it. But you do need to know what is the density of water in the system you're using so that you can convert that specific gravity to density. So let's look at an example. We'll take the specific gravity for a substance that has a density, we want the specific gravity, so that's what we're trying to find, for a substance that has a density of 3,000 kilograms per cubic meter. So we know rho, and then we know the density of water, and we want to find the specific gravity. So specific gravity is the density of the object divided by the density of water. So plugging in, we've got 3,000 kilograms per cubic meter divided by 1,000 kilograms per cubic meter. Our specific gravity is 3. You have some problems in the study guide on working with specific gravities and densities, so you really need to practice those. So fluids have internal pressure. I said earlier that a fluid is comprised of either of gases and liquids. And so pressure is force per unit area. So P equals F divided by A. This is a capital P, a capital F, and a capital A. Pressure is force divided by area. The pressure is measured in newtons per meter squared or pascals. Now we abbreviate pascals as PA, so capital P, little a. And that's 1 Pascal is the same thing as 1 Newton per meter squared. Sometimes we measure pressure in units of PSI, and that's short for pounds per square inch. If you've ever paid attention to the air pressure in your tires, what you look at are the pounds per square inch. And sometimes we measure air pressure in terms of atmospheres, where 1 atmosphere is 1.013 times 10 to the 5th newtons per meter squared. So we have a lot of different units that we measure pressure in. We have a variety of units to measure pressure in. It just depends on the application as to which one is the most useful. So a fluid exerts pressure in all directions. It pushes up, it pushes down, right, left. You would know this, and it's uniform in all directions if your fluid is at rest. So at rest, the pressure is perpendicular to any surface in contact with it, and it's at rest. So it's uniform, it's the same in all directions. You would know this if you've ever tried to walk in water. So maybe you've been out in the lake or something and you've tried to walk where the water is, say, up to your knees. It is really difficult because the water is pushing against you harder than the air is at your shoulders. And so you notice a difference. But if you were completely submerged underwater, your pressure would be equalized and be very easy to move around. So we've already said that pressure is force over area, but force is the weight of an object. So that could be the force. So mass times gravity over area. But the relationship between volume and mass is volume times density will give you the mass. So we've got volume times density times gravity over area. And we know that the volume is the cross-sectional area times the height of the object. So the areas will cancel out. And what we end up with for a fluid is that the pressure is equal to rho GH. P equals rho GH. Pressure equals density times the acceleration due to gravity times the depth of the fluid. Little h is the depth of the fluid. And let's see where we would use that. So P equals rho GH, you need to know that. Let's see how we can apply it. So we want to know the pressure at a depth of 2 meters in a vat of alcohol if alcohol has a density of 800 kilograms per cubic meter. So we know that H is 2 meters and that rho is 800 kilograms per cubic meter, and we want to find the pressure. Well, P equals rho GH. That's the only formula we've got relating all of that. So we'll write down our formula. P equals rho GH. And plug in. Rho was 800 kilograms per cubic meter, G is 9.8 meters per second squared, and H is 2 meters. So 2 times 9.8 times 800 gives us 15,680 newtons per meter squared, or pascals. You can write it either way. If we move on, we can talk about atmospheric pressure and gauge pressure. So the absolute pressure is atmospheric pressure plus the gauge pressure. When you are measuring pressure with any kind of gauge meter in normal everyday life, it is discounts the atmospheric pressure. And so if you wanted an absolute value of the pressure pushing on something, it would be a combination of those two values. So if your tire had a 32 psi pressure measurement, then it's 32 psi plus 14.7 psi for air pressure, which would give you 46.7 psi. So you have to be careful what pressure you're talking about. You need to be specific. Are we talking about atmospheric pressure, gauge pressure, or absolute pressure? To give you some idea of pressure in the human body, this is a table from the book. So your systolic and diastolic pressures are given, blood pressure in the large veins, inside the eye, spinal fluid if you're lying down, your bladder when it's full. No wonder you have to run, go use the bathroom. Or maybe you don't, but lots of us do. So depending on where you are, different pressures. All right, this is a graphic of a blood pressure cuff, and it talks about the systolic and diastolic pressure. I thought you might find it interesting. You maybe have wondered what they're listening for when they take your blood pressure. So let's talk about Pascal's principle. So Pascal's principle relates to hydraulic lifts for pushing fluids around in confined spaces. Pascal's principle says that when pressure is applied to a confined fluid, that pressure is transmitted throughout the fluid and it acts in all directions. So pressure in equals pressure out. That would be a mathematical statement of Pascal's principle if your fluid is confined. So what we have shown in figure 2 is a variable diameter pipe. So we have our input has a very small diameter and our output has a very large diameter. If you exert an input force on the small input area, you're going to create a pressure. Pressure is force divided by area. That'll be the input pressure. The output pressure will force up the brown piston on the right-hand side and create an output force. And again, output pressure will be, pressure is force over area, so output force divided by output area. Well, what's true for this is pressure in equals pressure out. Pressure in equals pressure out. So even though we've got a little input force, we're going to have a large output force because of Pascal's principle. Let's look at the math behind it. So pressure in equals pressure out, but pressure is force over area. So force in over area in equals force out over area out. So force in over force out equals area in over area out. If force in is little and area in is little and area out is big, then force out is big. because the ratios have to hold true. All right, maybe a numeric example would be easier. So I've got part of it worked out, and then we'll do the rest of it. Suppose we have a 2 Newton force pushing in on a plunger that's 1 centimeter across. So 1 centimeter is 0.01 meters, and the radius of that would be 0.005 meters. The diameter out is 3 millimeters across, so 0.003 meters. So the output radius is half of that, 0.0015 meters. And we want to find the output force. So this is a needle, all right? We're working with a needle. So needles, caulking guns, that kind of thing fall into this category. We know that pressure is force over area, that area is pi r squared for a circle, and that pressure in equals pressure out. So we had to start with finding the first two areas. Area in equals area out, so pi r squared in gave us 7.854 times 10 to the minus fifth meters squared, and area out gave us 7.069 times 10 to the minus 6 meters squared. So once we have those areas, we can use Pascal's principle. So pressure in equals pressure out, but pressure is force over area. So area in equals force in over area in equals force out over area out. Plug in our numbers. 2 newtons divided by 7.854 times 10 to the minus fifth meters squared equals the output force divided by 7.069 times 10 to the minus 6 meters squared. To find the force, you multiply both sides by the denominator that's on the right-hand side. So both sides get multiplied by 7.069 times 10 to the minus 6. It'll cancel, leaving force out by itself, and multiply by the numbers on the left. And so if you rearrange it, force out is 7.069 times 10 to the minus 6 times 2 divided by 7.854 times 10 to the minus 5th. When you punch all that into your calculator, being really careful, you end up with 0.180. So not very much at all. If you have trouble punching in numbers like 7.069 times 10 to the minus 6 into your calculator, or if when you punch it in you don't get the same answer I did, please ask me for help. It's easy to fix. So how do we measure pressure? Well, most of the time in the real world, people use a barometer. So lots of different devices, but barometers are typically used for air pressure. So pressure again is equal to rho GH, density times acceleration due to gravity times the height of the column of fluid. So what we use is usually you have a container of liquid. Mercury is most common because it's very dense. And then you have an inverted tube. So the tube has a vacuum in the closed end, and then the open end is down into the pool of mercury. So it's open down here. Air pressure pushes down. That forces the mercury to move up into the empty tube, and the height of the column is a measure of the air pressure, of the atmospheric pressure. So the height of that column, how high is it above the reservoir, will tell you what the air pressure is. And we can use P equals rho GH. This would be H. You can use H and G and rho in the right densities, the right units, to be able to convert a distance to a pressure. So we've got a diagram showing you high pressure compared to low pressure. So the blue arrows represent atmospheric pressure. High pressure, they are bigger arrows than for the low pressure. So it pushes down on the puddle of mercury, which forces the liquid up into the empty tube, and the column is longer. For a low pressure, the blue arrows are shorter. They don't push the liquid, which in this case should be mercury, up as high, and the column is shorter or lower. 1 atmosphere is 760 millimeters of mercury. If you made one out of water, the tube would have to be over 30 feet long. If you use pure alcohol, it would have to be more than 13 meters long. So we're talking a long way. They say Pascal made one using red wine, but he probably didn't have a vacuum in it. And so his wine wouldn't have gone up as high as you would imagine because there'd be a little trapped air inside. But still, it allows you to predict variations in atmospheric pressure. There are other kinds of barometers. There is an aneroid barometer, which has a vacuum chamber. It's a little disc down inside, and when air pressure changes, the volume of the chamber alters. High pressure, it is smaller. Low pressure, it is larger. And what that does is it moves the lever, which moves the spindle, which moves the pointer, and gives you a measure of the atmospheric pressure. In class or lab, we will do demonstrations with a glass jar and a candle, and also a soda can and some boiling water. So look for those demonstrations. I'm not sure if we'll do them in lab or class or both. I haven't decided yet. All right, so buoyant forces and Archimedes principle. So buoyancy is you feel lighter, something is supporting you. So Archimedes' principle states that any object partially or completely submerged in a fluid, fluid, so that means gases and liquids. So completely or partially submerged in a fluid will be buoyed up by a force equal to the weight of the displaced fluid. Now, for most of us, it's easier to think of displaced fluid when you put an object in a liquid. So in figure 6, we have a little gray weight hanging by a scale, and the reading is 7 kilograms. When you let that drop into, and you'll notice that the container of water is to the very tippy top right before there's a straw stuck in the side of the container for a spillway. So that if you have too much, instead of flowing over onto the tabletop, it's collected in the little watch glass off to the side. So the gray weight is above, not in the water yet, it's 7 kilograms. When we drop it into the water, the gray weight shows a 4 kilogram mass on the scale. What that tells me, the difference between 4 and 7 is 3 kilograms. What that tells me is that the water is helping to support it, that the water is reducing the mass, the weight, by 3 kilograms in this instance. And when we drop the weight into the water, since the container was full, it took the place of some of the liquid, and the extra liquid flowed out the side and was collected in this watch glass. And in fact, if we weigh that, we'll see its mass is 3 kilograms. So this 3 kilograms plus that 4 kilograms gives us our starting 7 kilograms. The volume of the gray weight is equal to the volume of 3 kilograms of water. So if we took the density of water and this mass, density is mass divided by volume, we could calculate the volume of the water and use it to figure out the volume of the weight if we wanted to. Volumetric displacement is used a lot of times when it's the easiest way to calculate a volume. So there's a relationship between displaced mass and the buoyant force. So the buoyant force is that upward force that supports any object when it's submerged in a fluid. Floaters. An object floats if its density is less than that of the fluid it's immersed in. So floaters displace enough fluid to equal their own mass. a floater will displace their own mass. So the mass of the object equals the mass of the displaced fluid. The mass of the object equals the mass of the displaced fluid if you're floating. So how do some things float when their densities are not less than the density of water? Aluminum has a density of 2.7 grams per cubic centimeter, and the density of water is only 1 gram per cubic centimeter. So why does an aluminum canoe float? Because the 2.7 grams per cubic centimeter is the density of the aluminum, not the density of the boat. To get the density of the boat, you would have to take the density is mass over volume, so you'd have to take the mass of the boat divided by the volume of the boat, and you would find out that if your canoe floats, the density of the canoe is less than 1 gram per cubic centimeter. So why do things sink? An object sinks if its density is greater than that of the fluid it's in. So the volume of the object equals the volume of the displaced fluid. Well, wait a minute. Some things float and sink. Submarines, for example. Well, a submarine changes its density. It has holding tanks, and it adds water to the holding tanks to increase its mass. And since density is mass divided by volume, they're able to sink. And when they want to float, they just force the water out. That reduces their mass, and they come up to the surface. Fish change their volumes using an air bladder. And in fact, humans change their volume when you want to float. So if you've ever tried to float, you will notice that what you do is you inflate your lungs just a little bit. If you completely exhale while you're trying to float, you will sink. So we change our volume. Submarines change their mass, people change their volume. Figure 7 shows you just a little graphic of the swim bladder on a fish. It's a little place where air can be held to change the density. So let's talk about Archimedes' principle. So if you have a low density object, this one's got holes in it, it's going to float fairly high. We'll assume our liquid is water. So gravity's pulling you down, the buoyant force is supporting you. If you float, then the mass of the displaced fluid is equal to the mass of the object. Suppose we have something that's a little denser. It's going to sit a little lower in the liquid. It's still floating, but you'll notice it has to displace it more liquid. You can see the red line is the line of the liquid when we had our least heavy object in, our least dense. The one with all the holes in it. And the middle one is our medium density object. And the one on the far right that looks like metal is our high density object. And you will notice it doesn't float, it is completely submerged. And in fact, the volume of the fluid above the red line would equal the volume of the object, because that's how much water was displaced, was forced up by the metal when it sank to the bottom. All right. I think we will stop there and pick up with our next video, because it's all about calculating using Archimedes' principle.